There is a boundary at the edge of our solar system that most people have never heard of, and what lies beyond it may be the most important discovery in the history of space exploration. Not important in the way that headlines use that word casually and without weight, but important in the way that changes how physicists understand the fundamental forces that govern the universe. Important in the way that makes scientists sit quietly in their offices for a long time after reading the data. Not because they are confused, but because they understand exactly what they are looking at, and it is nothing like what they were told to expect. Tonight, we are going to travel to a place that no human technology has ever imaged directly. A region so distant from Earth that the light we see in our night sky left the sun before the pyramids of Egypt were built, and it is still traveling. We are going to explore what happens when the sun's influence finally runs out, where the solar wind that has been blowing outward for 4.5 billion years finally exhausts itself and stops, and what NASA's instruments have detected lurking in the darkness on the other side of that boundary. What you are going to understand by the end of this is not just a geographical description of a distant region. You are going to understand why the shape of our solar system's edge is wrong, why the forces operating there defy the models that took decades to build, and why the data coming back from the most distant human-made objects ever launched is forcing a fundamental rewrite of heliophysics, the science of how the sun governs the space around it. The story begins with a boundary called the heliopause. This is the true edge of our solar system, not in the sense of where the last planet orbits, not in the sense of where the gravitational influence of the sun ends, but in the very specific sense of where the sun's physical presence, the bubble of charged particles it continuously exhales into space, finally meets the interstellar medium and can go no further. Inside the heliopause, you are in the sun's territory. Outside it, you are in the galaxy. And what NASA has found at that boundary and beyond it is stranger than nearly anyone predicted. To understand the magnitude of what has been discovered, you first have to understand how far away this boundary actually is. The average distance from Earth to the Sun is defined as 1 astronomical unit. You can think of 1 astronomical unit as the baseline unit of measurement for our solar system, roughly 93 million miles. Jupiter, the largest planet in our solar system, orbits at about 5 astronomical units from the Sun. Neptune, the most distant of the 8 classical planets, orbits at roughly 30 astronomical units. The heliopause, the actual edge of the Sun's physical bubble, sits somewhere between 100 and 123 astronomical units from the Sun, depending on the direction you are measuring. A fact which turns out to be deeply important and which we will return to later. 123 astronomical units. To translate that into something your nervous system can process, consider that light, moving at approximately 186,000 miles per second, takes about 8 minutes and 20 seconds to travel from the Sun to Earth. That same light, continuing outward, takes over 17 hours to reach the heliopause. If you were traveling in the fastest spacecraft ever built, the Parker Solar Probe at its closest approach to the Sun moves at roughly 430,000 miles per hour. At that speed, it would still take you more than 600 years to reach the heliopause. This is how far away the edge of our solar system is, and we have instruments there right now. If you find yourself genuinely astonished by that fact, if you are sitting with the weight of what it means for humanity to have reached beyond the outer boundary of the Sun's domain, please take a moment and consider subscribing to this channel. The goal here is to share exactly this kind of depth, this kind of genuine reckoning with the scale of what our species has achieved with as many curious people as possible. Your support makes that possible. The instruments at the heliopause belong to two spacecraft, Voyager 1 and Voyager 2. Launched in 1977, these two probes have been travelling away from Earth for nearly 5 decades. Voyager 1 crossed the heliopause in August of 2012, becoming the first human-made object to enter interstellar space. Voyager 2 crossed the heliopause in November of 2018, following a different trajectory that took it through a different part of the boundary. Both spacecraft are still operational. Both are still sending data back to Earth. And the data they have been transmitting over the last several years, combined with new analysis from instruments aboard other NASA missions, including the Interstellar Boundary Explorer, has revealed something that is fundamentally at odds with the theoretical framework that heliophysicists spent the better part of 40 years constructing. The theoretical framework was called the heliosphere model, and it predicted that the sun's bubble would have a roughly comet-like shape. The reasoning was intuitive and physically sound. The sun and our entire solar system are not stationary. We are moving through the galaxy at approximately 450,000 miles per hour in the direction of the constellation Hercules. As we move through the interstellar medium, the incoming interstellar gas and dust should pile up on the leading edge of our bubble, compressing it, while the trailing edge should stretch out behind us like the tail of a comet. The models predicted a blunt, rounded nose on the sunward-facing side and a long extended tail, sometimes called the heliotail, streaming out for potentially hundreds, possibly even thousands, of astronomical units behind us. This model was not a fringe hypothesis. It was the consensus view, supported by simulations, backed by decades of theoretical work, and considered essentially established science. What the Voyager spacecraft found when they actually crossed the boundary, and what subsequent analysis has continued to reveal, is that this picture is wrong in ways that strike at the assumptions underlying the entire model. The discrepancy is not minor, not a small refinement at the edges of the theory, but a structural contradiction that requires rethinking the basic physics of how the heliosphere interacts with the surrounding interstellar environment. To understand exactly what was found and why it matters, we need to understand what the solar wind actually is, how it behaves, and what should happen to it when it reaches the boundary of its domain. The sun is not a static object. Every second of every day, it is losing mass. It does this through two mechanisms. The first is radiation, the electromagnetic energy that streams outward in all directions as photons, the light and heat and ultraviolet and X-rays that power the inner solar system. The second mechanism is the solar wind, a continuous outward flow of charged particles, primarily protons and electrons, that are ejected from the sun's outer atmosphere, the corona, and stream outward in all directions at speeds ranging from roughly 250 miles per second during calm periods to over 500 miles per second during active periods. The solar wind is not a gentle breeze in the way the name implies. It is a supersonic flow of plasma, magnetized and energetic, carrying with it a portion of the sun's own magnetic field, stretched outward into a vast structure called the heliospheric magnetic field. This solar wind does not flow outward indefinitely at the same speed. At some point, it encounters the pressure of the interstellar medium pushing inward, and it must slow down. The place where it first slows from supersonic to subsonic speeds is called the termination shock. Both Voyager spacecraft crossed the termination shock before they reached the heliopause. Voyager 1 crossed the termination shock in 2004 at a distance of approximately 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at approximately 84 astronomical units, and this discrepancy, 10 astronomical units of difference for two spacecraft heading in different directions, was itself an early hint that the heliosphere was not the symmetric, neatly shaped structure the models assumed. Between the termination shock and the heliopause lies a region called the Helios Heath. This is the zone where the solar wind, having been slowed to subsonic speeds, piles up and becomes turbulent, compressed and heated, mixing with neutrals that have drifted in from the interstellar medium and become partially ionized by the sun's ultraviolet light. The heliosheath is not a thin boundary layer. It is a thick, complex region that both Voyager spacecraft spent years traveling through before reaching the heliopause. Voyager 1 spent roughly 8 years in the heliosheath before crossing the heliopause. Voyager 2 spent approximately 11 years in that transition zone. The difference in crossing times, combined with the different distances at which they each encountered the termination shock, told scientists something important before they even had the heliopause crossing data in hand. The heliosphere was not shaped the way the models said it should be, but it was the data from the heliopause crossings themselves and the measurements made in the interstellar medium just beyond them that delivered the most significant challenge to the consensus model. And to appreciate exactly what was found, we need to understand one more piece of background physics, a phenomenon called the neutral hydrogen wall, and the behavior of magnetic fields at the boundary between the heliosphere and the interstellar medium. This background is not a detour. It is the key that makes the discoveries legible. The interstellar medium is not empty. Between the stars, space is filled with a thin, diffuse mixture of gas and dust. In the vicinity of our solar system, this interstellar medium is predominantly hydrogen, much of it in neutral atomic form rather than ionized plasma. This matters because neutral particles, unlike charged plasma, are not deflected by magnetic fields. They can drift across magnetic boundaries as if those boundaries do not exist. As the interstellar medium flows past the outer surface of the heliosphere, some of these neutral hydrogen atoms drift inward, crossing the heliopause and entering the Helios Heath. There they encounter the solar ultraviolet radiation, which ionizes them, converting them into protons and electrons that are then swept up by the solar wind. This process of charge exchange, where an incoming neutral picks up an electron from an outgoing solar wind ion and the two effectively swap identities, has profound consequences for the structure and energy budget of the outer heliosphere. One consequence is the creation of a population of energetic neutral atoms. When a fast-moving solar wind ion exchanges a charge with a slow-moving neutral from the interstellar medium, the result is a fast-moving neutral atom traveling in the direction the original solar wind ion was going, and a new slow-moving ion that gets picked up by the solar wind. The fast neutral atom is not constrained by magnetic fields and travels in a straight line from the point of its creation. This means it can travel all the way back to the inner solar system without being deflected, and it can be detected. This is how the Interstellar Boundary Explorer, launched in 2008 into an orbit around the inner solar system, has been able to map the outer heliosphere without actually being there. It is essentially a camera that uses energetic neutral atoms as photons, building images of structures hundreds of astronomical units away from a vantage point, only a fraction of 1 astronomical unit from the Sun. Between 2009 and 2024, the interstellar boundary explorer accumulated enough of these energetic neutral atom detections to build genuine maps of the heliosphere's outer structure. The maps were not perfect. The instrument was working at the limits of what was physically detectable, counting particles that had travelled nearly 100 astronomical units in straight lines and arrived at the detector one at a time over years of observation. But the maps were real, and they were detailed enough to test the comet-shaped heliosphere hypothesis directly. What they showed was that the elongated tail the models predicted, the structure that should have stretched hundreds or thousands of astronomical units behind the sun's direction of travel, was not there. Or at least, it was not there in the way the models said it should be. The energetic neutral atom maps from the interstellar boundary explorer showed a heliosphere that appeared more spherical, or possibly lobe-shaped, than comet-like. The supposed heliotail, instead of being a single elongated structure, appeared to split into two broad lobes extending in different directions, shaped less like a comet tail and more like the croissant-shaped structure that a competing theoretical model, developed independently by a group of researchers who had long argued against the comet model, had actually predicted. The debate between these two camps, the comet tail faction and the croissant faction, had been running in the heliophysics community for years before the interstellar boundary explorer data arrived. The data did not fully settle the debate because interpreting energetic neutral atom maps requires assumptions about what the particles experienced along their 100 astronomical unit journey, and different assumptions led to different conclusions. But the data decisively weakened the clean comet tail picture and gave serious observational weight to the idea that the heliosphere's shape was something fundamentally different from what most textbooks described. The shape of the heliosphere is not an abstract aesthetic question. It matters because the shape reflects the underlying physics of how the solar wind pressure, the interstellar magnetic field, and the interstellar plasma flow interact at the boundary. If the shape is wrong, something in the force balance is wrong. And if the force balance is wrong, the models that describe how galactic cosmic rays penetrate the heliosphere are wrong. The models that describe how the sun's magnetic field connects to the galaxy are wrong. And potentially the models that describe how our solar system has been shielded from the broader galactic environment over billions of years are wrong. Those are not trivial errors. Those are errors that propagate outward into questions about the long-term habitability of Earth and the conditions that allowed life to develop here over 4 billion years. Now consider what the Voyager spacecraft found when they actually crossed the heliopause, the physical boundary itself, rather than imaging it remotely. Voyager 1's crossing in 2012 was detected through a sudden and dramatic change in the particle environment surrounding the spacecraft. Inside the heliosphere, the dominant particles were those of the solar wind, low-energy protons and electrons flowing outward from the sun, along with a population of anomalous cosmic rays, particles that had been accelerated at the termination shock. Outside the heliosphere in true interstellar space, those solar wind particles and anomalous cosmic rays essentially vanished within days of the crossing, replaced by a completely different population of galactic cosmic rays, high-energy particles accelerated by distant supernovae and other energetic events throughout the galaxy, arriving from all directions with a remarkably isotropic distribution. The transition was not gradual, it was abrupt, occurring over a period of just a few days, suggesting the heliopause was a sharper, more defined boundary than many models had assumed. But the magnetic field did something unexpected. The models predicted that when Voyager 1 crossed from the heliosphere into interstellar space, it would detect a significant change in the direction of the magnetic field. Inside the heliosphere, the magnetic field is dominated by the heliospheric magnetic field, the Sun's own field, dragged outward and wound into a spiral pattern by the Sun's rotation. Outside, in the local interstellar medium, the magnetic field should be oriented in a completely different direction, set by the large-scale structure of the galaxy's magnetic field in this region of space. The crossing in the model should have produced a clear directional shift in the field. It did not, or rather it produced a much smaller directional shift than expected. The magnetic field outside the heliopause was oriented more closely to the field inside than the standard models predicted, suggesting either that the local interstellar magnetic field in this region of space is aligned more closely with the heliospheric field than chance would suggest, or that the boundary region was compressing and reorganizing the field in ways the models did not capture, or that the Voyager 1 crossing occurred in a region of the heliopause that was structurally different from a typical crossing point. This magnetic field puzzle was not resolved by Voyager 2's crossing 6 years later. In fact, Voyager 2's data added new complexity. Voyager 2 crossed the heliopause at a different point in the southern hemisphere of the heliosphere rather than the northern, and at a slightly different distance, approximately 119 astronomical units, compared to Voyager 1's crossing at approximately 122 astronomical units. The difference in crossing distance, 3 astronomical units, was smaller than many models predicted for the difference between the nose of the heliosphere and other directions. But Voyager 2 measured something at its crossing that Voyager 1 could not because of a difference in their onboard instrument suites. Voyager 2 carried a working plasma science instrument. Voyager 1's plasma science instrument had failed decades earlier. The plasma data from Voyager 2's heliopause crossing revealed that the temperature of the plasma in the heliosheath just inside the boundary was significantly higher than the models had predicted, hotter by a factor that suggested energy was being deposited into the heliosheath from outside, from the interstellar medium through the boundary, in quantities that the standard models of heliopause physics did not account for. Hot plasma inside the boundary, a magnetic field that did not shift direction the way it should, a heliosphere that does not have the tail the models predicted. Each of these anomalies taken individually might be explained away as local conditions, measurement uncertainty, or edge cases in the models. But taken together, they paint a picture of a boundary region and an outer heliosphere that are fundamentally more dynamic, more magnetically complex, and more deeply coupled to the surrounding interstellar environment than the theoretical framework was built to describe. And this is before accounting for what the interstellar boundary explorer found when it looked not just at the shape of the heliosphere, but at the ribbon. The ribbon is perhaps the single most startling discovery to come from the Interstellar Boundary Explorer mission, and it deserves its own extended discussion, because its implications extend far beyond the simple question of what our solar system's edge looks like. When the Interstellar Boundary Explorer began returning its first maps of energetic neutral atom emissions in 2009, scientists expected to see a broad, relatively uniform glow from the heliosphere's outer regions, perhaps with some brighter and dimmer areas corresponding to where the solar wind was more or less compressed. What they did not expect, and what immediately dominated the maps, was a narrow, bright arc of energetic neutral atom emission curving across the sky in a band that encircled the entire heliosphere. They called it the ribbon. It was not predicted by any of the standard models. It appeared out of nowhere, fully formed, in the very first maps the instrument produced. The ribbon is not subtle. It is the brightest feature in the energetic neutral atom sky, roughly 2 to 3 times brighter than the surrounding heliosphere, and it is geometrically striking, a narrow band only a few tens of degrees wide that curves completely around the sky in a great circle. The orientation of this great circle is not random. The plane of the ribbon is perpendicular to the direction of the local interstellar magnetic field. This geometric relationship was recognized early and is one of the most important clues to understanding what the ribbon actually is, because it connects the ribbon directly to the structure of the interstellar magnetic field in our local neighborhood of the galaxy. Several competing explanations for the ribbon emerged in the years after its discovery. One leading explanation proposed that the ribbon forms where the interstellar magnetic field is tangent to the heliopause, meaning where the field lines run parallel to the boundary surface rather than meeting it at an angle. In those regions, charge-exchanged neutral atoms that have escaped the heliosphere and travel outward into the interstellar medium are quickly reionized by the interstellar radiation field and picked up by the local interstellar magnetic field. If those newly ionized particles then undergo another charge exchange, they can produce a second generation of energetic neutral atoms that travel back toward the inner solar system and are detected by the Interstellar Boundary Explorer. This two-step retention model would explain why the ribbon marks the regions where the interstellar magnetic field is tangent to the heliopause, because those are the regions where the reionized particles are most efficiently trapped and can undergo the secondary charge exchange. This explanation has received significant modeling support, but it requires a very specific geometry of the local interstellar magnetic field, and constraining that geometry is itself a major unsolved problem in heliophysics. What the ribbon tells us, regardless of which specific formation mechanism turns out to be correct, is that the heliosphere and the local interstellar magnetic field are deeply coupled, not just at the boundary, but in a way that creates large-scale organized structures visible across the entire sky. The heliosphere is not simply a bubble sitting passively in the interstellar medium. It is an object that is being actively shaped, compressed, and organized by the magnetic environment around it, and its own energetic particle output is in turn being organized and reflected back by that environment. The Sun's bubble and the galactic neighborhood it occupies are in a continuous, dynamic conversation, exchanging energy and particles across the heliopause in both directions, and the ribbon is the visible signature of that exchange. To understand why this matters beyond the immediate scientific questions, you need to understand something about where our solar system currently sits in the galaxy and how unusual that location may be. The Sun does not reside in a typical patch of interstellar space. We are currently passing through a region called the local interstellar cloud, sometimes referred to as the local fluff, a diffuse, warm, partially ionized region of gas roughly 30 light-years across. The local interstellar cloud is itself embedded within a much larger structure called the local bubble, a vast cavity in the interstellar medium roughly 1,000 light-years across that was carved out by a series of supernova explosions occurring over the past 10 to 20 million years. The interior of the local bubble is filled with hot, low-density plasma, significantly less dense than the average interstellar medium in the galaxy. We happen to be living inside this cavity, near one of its inner clouds, at a particular moment in the Sun's 4.5 billion-year journey around the galaxy. This is not a permanent address. The Sun moves through the galaxy, and the interstellar environment it passes through changes over time. At some point in the past, the Sun was moving through denser interstellar material. At some point in the future, it may enter a region where the interstellar medium is significantly denser or significantly more magnetized or moving at a different relative velocity. When that happens, the heliosphere will change shape and size in response. A denser interstellar medium pressing inward would compress the heliopause to smaller distances from the Sun, potentially reducing the shielding that the heliosphere provides against galactic cosmic rays. More galactic cosmic rays reaching the inner solar system means more energetic particles striking Earth's atmosphere, with potential consequences for atmospheric chemistry, cloud formation, and over geological timescales, possibly climate. This connection between the heliosphere's size and shape and the long-term habitability of Earth is one of the reasons NASA considers the study of the heliosphere's outer boundary to be not merely an abstract, scientific exercise, but a question with genuine relevance to understanding the conditions that have allowed life on this planet to persist for billions of years. The heliosphere is, in a very real physical sense, our first line of defense against the galaxy. It is the shield that stands between the inner solar system and the full intensity of the galactic cosmic ray environment. And NASA's data from the outer boundary is revealing that this shield is more complex, more dynamic, and more sensitive to external conditions than we previously understood. Now, we need to talk about what Voyager 1 detected in the years after its heliopause crossing, because the post-crossing data has raised questions that go beyond the structure of the heliosphere and touch on the fundamental physics of how magnetic fields behave at plasma boundaries. After crossing the heliopause in 2012, Voyager 1 entered what scientists expected to be a relatively quiet region of interstellar space. The immediate vicinity beyond the heliopause should be the undisturbed local interstellar medium, shaped primarily by the large-scale galactic magnetic field and the slow, steady flow of interstellar gas moving past the outside of the heliosphere. What Voyager 1 found instead was a region that was anything but quiet, a zone of elevated electron density, fluctuating magnetic fields, and particle distributions that suggested the interstellar medium just outside the heliopause had been significantly disturbed and organized by its proximity to the heliosphere. The electron density measurements were particularly striking. Inside the heliosphere, the plasma density decreases with distance from the Sun as the solar wind expands into ever larger volumes of space. At the heliopause crossing, scientists expected to find a transition to the local interstellar medium electron density, which theoretical models and indirect observations had estimated at somewhere between 0.04 and 0.1 electrons per cubic centimeter. What Voyager 1 measured was significantly higher than the lower end of those estimates, and what was even more informative was what happened when the Sun produced coronal mass ejections, massive eruptions of plasma and magnetic field that sent pressure waves propagating outward through the solar wind. Those pressure waves traveled all the way through the heliosphere, crossed the heliopause, and propagated into the interstellar medium outside, where they caused the local plasma to oscillate at a characteristic frequency. By measuring those oscillations, scientists could determine the local electron density directly, And what they found was that the interstellar medium just outside the heliopause has a density of approximately 0.05 electrons per cubic centimeter, rising slightly with distance as Voyager 1 moved farther from the boundary. This was a real measurement of the interstellar medium, not a model prediction, and it was the first direct sampling of that environment in human history. But beyond the electron density, the nature of the magnetic fluctuations. Voyager 1 encountered in the interstellar medium raised a deeper puzzle. The region outside the heliopause was not magnetically smooth. It contained structures, variations in field strength and direction that implied turbulence and possibly organized flows in the interstellar plasma. Some of these structures appeared to be associated with the heliosphere's influence extending outward into the interstellar medium, a kind of magnetic wake or disturbance zone created by the interaction between the heliosphere's outer surface and the incoming interstellar flow. This zone of disturbed interstellar medium surrounding the heliopause is sometimes called the hydrogen wall on the upwind side, where incoming interstellar hydrogen piles up and is decelerated before it enters the heliosphere, and a less well-characterized disturbed region on the downwind side. Voyager 1, traveling in the upwind direction where it crossed the heliopause, was not ideally positioned to sample the hydrogen wall directly, but its measurements of the disturbed interstellar plasma in its vicinity were consistent with the presence of a boundary interaction region significantly more extended and dynamically complex than the models had envisioned. What Voyager 2 added, crossing the heliopause 6 years later in a different direction and with its plasma instrument intact, was a crucial piece of data that confirmed and extended what Voyager 1 had suggested. Voyager 2's plasma instrument measured the temperature of the plasma immediately inside the heliopause in the inner heliosheath at approximately 30,000 to 50,000 degrees Kelvin in certain particle populations, which was broadly consistent with expectations, but it also measured the plasma just outside the heliopause in the interstellar medium, and found that the temperature there was significantly higher than the models of the undisturbed local interstellar medium predicted, on the order of 30,000 to 40,000 degrees Kelvin, rather than the few thousand degrees that theoretical models of the local interstellar cloud had assumed. This elevated temperature suggested that the interstellar medium in the immediate vicinity of the heliopause had been heated by its long interaction with the heliosphere, or that the local interstellar cloud itself is hotter than previously believed, or both. The discrepancy in temperature had cascading implications. If the local interstellar medium is significantly hotter than the models assumed, the pressure balance at the heliopause is different from what was calculated. The shape of the heliosphere is determined by different force ratios, and the rate at which neutral hydrogen can penetrate the heliopause is altered. Each of these downstream effects touches a different aspect of heliosphere physics, and each one requires the models to be revised. The revisions are not catastrophic for the overall framework, but they are substantial enough that heliophysicists have described the post-Voyager theoretical situation as a period of fundamental model reconstruction rather than incremental refinement. There is another discovery from the outer heliosphere data that has received less public attention than the ribbon or the Voyager crossing anomalies, but which may ultimately prove to be the most scientifically significant of all. It concerns the behavior of the anomalous cosmic rays at the termination shock, and what their behavior implies about where and how particle acceleration occurs at the boundary of the heliosphere. Anomalous cosmic rays are a specific class of energetic particle that exists only inside the heliosphere. They are created when neutral atoms from the interstellar medium drift into the heliosphere, become ionized, are picked up by the solar wind, and are then accelerated to high energies at the termination shock. For decades, the Standard Model held that the termination shock was the primary site of anomalous cosmic ray acceleration, and that the particles accelerated there would be distributed more or less uniformly around the termination shock surface. When Voyager 1 crossed the termination shock in 2004, scientists expected to find the intensity of anomalous cosmic rays increasing dramatically because they were approaching and then crossing the acceleration site. Instead, the anomalous cosmic ray intensity increased slightly at the termination shock crossing, but then continued to increase for years afterward as Voyager 1 travelled through the heliosheath toward the heliopause. The particles were not being accelerated primarily at the termination shock. They were more intense deeper in the heliosheath, closer to the heliopause. This meant the acceleration was happening somewhere else, or through some process distributed throughout the heliosheath rather than concentrated at the shock surface. Voyager 2's termination shock crossing 3 years later in a different location confirmed the anomaly. The anomalous cosmic ray intensities at Voyager 2's crossing were also not at their peak at the shock, and the spatial distribution of the particles was different from what the Standard Model predicted. Something was wrong with the fundamental picture of how particle acceleration works at the termination shock, and the competing explanations that emerged in the years following these crossings, involving magnetic reconnection in the heliosheath, stochastic acceleration in turbulent plasma, and the role of the heliopause itself as a secondary acceleration site, have not yet converged on a consensus. What the data had done was break the simple model and replace it with a much more complex and uncertain picture of a heliosheath filled with accelerating, turbulent plasma doing things that nobody fully predicted. The turbulence in the heliosheath is not simply an inconvenient complication for theorists. It is a physical reality with direct consequences for what reaches the inner solar system and ultimately what reaches Earth. Galactic cosmic rays, the high-energy particles accelerated by supernovae and other violent events throughout the galaxy, must pass through the heliosheath and the termination shock before they can reach the planets. The heliosheath acts as a partially effective shield against these particles, scattering and slowing them as they diffuse inward through the turbulent magnetized plasma. The more turbulent the heliosheath, the more effective the shielding. The less turbulent, the more galactic cosmic rays penetrate to the inner solar system. And what the Voyager data has revealed is that the turbulence in the heliosheath is not uniform, not static, and not well described by the simplified diffusion models that space weather scientists have used for decades to predict cosmic ray fluxes at Earth. This has practical consequences that extend far beyond academic heliophysics. Galactic cosmic rays are a significant radiation hazard for astronauts traveling beyond the protection of Earth's magnetosphere. The models used to assess that hazard and to plan the radiation shielding requirements for crewed missions to the Moon and eventually to Mars are built on assumptions about how galactic cosmic rays are modulated by the heliosphere. If those modulation models are wrong, the radiation environment predictions for deep space missions may be wrong, and the consequences of that error are not theoretical. They are measured in the biological dose received by human beings spending months in deep space. NASA's ongoing effort to refine the heliosphere models is therefore directly connected to the agency's ability to safely plan and execute the crewed exploration missions that define its long-term agenda. The connection between heliosphere science and human spaceflight safety was not always recognized as clearly as it is today. For most of the history of space exploration, galactic cosmic ray modulation was treated as a background parameter, something to be measured and accounted for, but not a primary driver of mission design. That began to change as the duration and ambition of planned missions increased. A 6-month transit to Mars, with the crew spending that entire time outside the Earth's protective magnetosphere, exposed to the full galactic cosmic ray flux modulated only by the heliosphere, represents a radiation environment significantly more challenging than anything encountered during the Apollo missions to the Moon. And the longer the mission, the more important it becomes to accurately predict not just the average galactic cosmic ray flux, but its variability, its response to solar activity, and its dependence on the heliosphere's structure in ways that the pre-Voyager models could not fully capture. But let us return to the data itself, because there is another layer of discovery from the outer heliosphere that takes the story in a direction that nobody anticipated when the Voyager program was conceived in the 1970s. In the years since the Voyager heliopause crossings, scientists analyzing the full dataset from both spacecraft have identified a puzzling asymmetry in the structure of the heliosphere that goes beyond the simple difference in crossing distances between the two probes. The heliosphere is not just slightly asymmetric, with one side a little closer to the Sun than another. It appears to be fundamentally lopsided in a way that reflects a complex interaction between the solar wind, the interstellar magnetic field, and the direction of the interstellar flow, and the degree of that lopsidedness changes over time in ways that are coupled to the solar activity cycle. The Sun's activity follows an approximately 11-year cycle, moving from solar minimum, when sunspot numbers are low and the solar wind is relatively steady and slower, to solar maximum, when sunspot activity peaks. The solar wind becomes more variable and faster on average, and coronal mass ejections are more frequent. This cycle modulates the total pressure of the solar wind, which in turn modulates the size and shape of the heliosphere. During solar maximum, the increased solar wind pressure pushes the termination shock and heliopause slightly farther out from the Sun. During solar minimum, reduced solar wind pressure allows the interstellar medium to press the boundaries slightly inward. The heliosphere breathes, expanding and contracting with the solar cycle, and the amplitude of that breathing is on the order of several astronomical units at the termination shock and somewhat less at the heliopause. What is more interesting than this expected breathing is the evidence, drawn from the Interstellar Boundary Explorer's multi-year energetic neutral atom maps, that the heliosphere does not breathe uniformly in all directions. The response of the heliosphere to solar cycle variations appears to be different on the nose side, where the interstellar flow compresses the boundary, than on the flanks and tail, where the geometry is different and the interstellar magnetic field plays a different role. This anisotropic breathing means that the shape of the heliosphere is not just lopsided in a static sense, but morphs over time in a complex, direction-dependent way that requires models significantly more sophisticated than the simple pressure balance calculations that defined the field for decades. The Interstellar Boundary Explorer's observations have been particularly revealing in this regard because the spacecraft has now accumulated more than 15 years of continuous energetic neutral atom maps, spanning more than one complete solar cycle. This time baseline has allowed scientists to watch the heliosphere evolve, to track how changes in solar wind output propagate outward to the termination shock and ultimately influence the energetic neutral atom emission from the helios sheath. The propagation is not instantaneous. A change in solar wind pressure at 1 astronomical unit takes roughly 1 to 2 years to reach the termination shock at 90 astronomical units, and the resulting change in energetic neutral atom emission takes additional time to propagate back to the interstellar boundary explorers' detectors in the inner solar system. The maps, therefore, show the heliosphere not as it is now, but as it was 1 to several years ago, a time delay that scientists must carefully account for when interpreting the data and connecting it to the solar conditions that caused it. This time delay is itself a form of looking back in time, a modest version of the same principle that makes astronomy inherently historical. When you look at a star, you are seeing it as it was years or centuries ago because light travels at a finite speed. When the interstellar boundary explorer maps the helios sheath, it is seeing conditions that existed there 1 to 3 years in the past. When Voyager 1 sends back data from its current position, now more than 160 astronomical units from the Sun, that data has been traveling for more than 22 hours before it arrives at the deep space network antennas on Earth. And the plasma and magnetic field conditions Voyager 1 is sampling right now reflect the interstellar medium as it exists in one small point along one narrow trajectory through space, a single thread of in situ measurement in a vast and largely unmeasured environment. This sparseness of measurement is one of the fundamental challenges facing heliosphere science. We have exactly 2 data points of in situ measurement beyond the heliopause, Voyager 1 and Voyager 2, traveling in 2 directions out of a continuous sphere of possible directions. We have remote sensing maps from the interstellar boundary explorer that cover the entire sky but cannot resolve fine structure and cannot directly measure plasma properties. We have theoretical models that are now known to be wrong in important ways, and we have a growing archive of data from both sources that is revealing the heliosphere to be more complex, more dynamic, and more tightly coupled to its galactic environment than any of the models predicted. The science is at an extraordinary juncture, where enough has been discovered to know that the old framework is inadequate, but not enough has been measured to know with confidence what the correct framework should be. It is worth pausing here to consider what it actually means to operate the Voyager spacecraft in their current condition, because the operational reality of maintaining contact with these probes provides its own kind of awe. Separate from the scientific discoveries, Voyager 1 and Voyager 2 were launched in 1977, which means the engineering teams at NASA's Jet Propulsion Laboratory are currently operating spacecraft that are nearly 50 years old, running on technology designed in the early 1970s, communicating across distances so vast that a radio signal traveling at the speed of light takes more than 22 hours to reach Voyager 1 and another 22 hours to return. Any command sent to Voyager 1 will not receive a response for more than 44 hours. Any anomaly that develops on the spacecraft must be diagnosed and addressed under those communication constraints, with no possibility of real-time intervention. The power source for both spacecraft is a radioisotope thermoelectric generator, a device that converts heat from the radioactive decay of plutonium-238 into electricity. The plutonium was loaded into the generators before launch, and it has been decaying ever since. The half-life of plutonium-238 is approximately 87.7 years, which means that after nearly 50 years of operation, the generators are producing roughly 33% less power than they did at launch. The spacecraft began their missions with roughly 470 watts of electrical power available. Today, each spacecraft has roughly 250 to 270 watts, and that number continues to decline by roughly 4 watts per year. To manage this declining power budget, NASA engineers have been systematically shutting down instruments and heaters over the decades, making careful choices about which scientific measurements are most valuable and which systems can be sacrificed to keep the most critical ones running. In 2023, Voyager 1 experienced a significant anomaly when the flight data system, one of the 3 onboard computers, began producing garbled data that could not be interpreted by the ground teams. For 5 months, engineers at the Jet Propulsion Laboratory worked methodically to diagnose the problem across that 44-hour round-trip communication delay, eventually determining that a single memory chip in the flight data system had failed, corrupting the code stored in that location. The solution required rewriting the affected software and distributing it across other memory locations on the chip in fragments small enough to avoid the damaged section. The reprogramming commands were sent across more than 160 astronomical units of empty space, and they worked. Voyager 1 resumed normal science operations in the summer of 2024. That this was accomplished at all with 50-year-old hardware across distances that dwarf human comprehension, using a team of engineers, some of whom were not yet born when the spacecraft launched, is a testament to something about human persistence and ingenuity that deserves to be held alongside the scientific discoveries themselves. The recovery of Voyager 1 in 2024 was not just an engineering triumph. It was a reminder that the data these spacecraft return is irreplaceable in a way that has no parallel in modern science. There is no other instrument, no planned mission, no theoretical substitute for the direct in situ measurement of the interstellar medium that only the Voyager spacecraft can provide. The next mission, capable of reaching the heliopause and beyond, if one were launched today, would not arrive at the termination shock for roughly 20 to 30 years, depending on its trajectory and velocity. It would not cross the heliopause for perhaps 35 to 40 years after that. The scientists who would analyze that data have not yet begun their careers. The Voyager spacecraft are therefore not historical artifacts operating on borrowed time. They are the only instruments humanity currently has at the frontier of interstellar space, and every day they continue to function is a day of irreplaceable scientific measurement that can never be recovered if the spacecraft falls silent. This irreplaceability has given the Voyager extended mission a quality of urgency that the original mission designers could not have foreseen. When Voyager 1 and Voyager 2 were launched in 1977, their primary mission was to conduct flybys of Jupiter and Saturn, with Voyager 2 continuing on to Uranus and Neptune. The interstellar mission was not the original objective. It was a bonus, an extraordinary bonus that nobody knew in 1977 would still be producing fundamental discoveries nearly half a century later. The longevity of the spacecraft, the longevity of the plutonium power sources, and the longevity of the deep space network infrastructure that maintains contact with them have together created a scientific program that has outlasted the careers of most of the people who built it, and that continues to produce surprises that reshape our understanding of the solar system's place in the galaxy. There is a parallel history running alongside the Voyager story that has not received the attention it deserves, and it concerns the role of the New Horizons spacecraft in heliosphere science. New Horizons was launched in January of 2006, primarily to conduct the first close flyby of Pluto, which it accomplished in July of 2015 with extraordinary success. After the Pluto flyby, New Horizons continued outward into the Kuiper Belt, conducting a flyby of the Kuiper Belt object Arrokoth in January of 2019, and it continues to travel outward today. New Horizons is currently at approximately 60 astronomical units from the Sun, still well inside the termination shock, but it is travelling in a direction that will eventually take it toward the heliopause and potentially into interstellar space decades from now. What makes New Horizons relevant to the heliosphere story right now, before it reaches the outer boundary, is what it has been measuring in the outer heliosphere during its long cruise through the Kuiper Belt. New Horizons carries an instrument called the Student Dust Counter, which has been measuring the density of dust particles in the outer solar system continuously since launch. It also carries ultraviolet spectrographs that have been used to measure the diffuse ultraviolet background light filling the solar system. And in 2021, a team of scientists analyzing New Horizons ultraviolet data announced a result that has sparked considerable debate and remains unresolved. They reported that after accounting for all known sources of ultraviolet light in the outer solar system, including distant galaxies, stars, and diffuse emission from known interstellar clouds, there remained a residual background of ultraviolet light that could not be attributed to any known source. This excess ultraviolet background, which they estimated at roughly double the expected level, implied the existence of an unknown source of ultraviolet emission, either within the solar system or in the near interstellar environment. The implications of this result, if confirmed, are profound. An unexplained source of ultraviolet background radiation at that level would suggest either that there is a population of faint, unresolved galaxies significantly more numerous than current galaxy count models predict, or that there is some local source of ultraviolet emission in the outer heliosphere or near interstellar medium that produces radiation at levels our models do not account for. The latter possibility connects directly to the broader heliosphere story, because the outer heliosphere and the heliopause region are known to produce ultraviolet emission through processes involving hydrogen charge exchange and energetic particle interactions. If those processes are more energetically significant than the models predict, the excess ultraviolet background measured by New Horizons could be a manifestation of the same systematic underestimation of heliosphere boundary physics that the Voyager and Interstellar Boundary Explorer data have revealed through completely independent measurements. This convergence of anomalies from multiple independent instruments, each measuring different physical quantities through different techniques, all pointing toward the same conclusion that the outer heliosphere and its interaction with the interstellar medium are more energetically significant and more physically complex than the models assumed, is what transforms what might otherwise look like a collection of isolated puzzles into something more coherent and more important. Science progresses most powerfully not when a single experiment overturns a theory, but when multiple independent lines of evidence converge on the same incompleteness in the theoretical framework. That is precisely the situation heliosphere science finds itself in today, and it is the reason why the field is experiencing what scientists describe as a period of genuine excitement, the kind that comes not from having answers, but from having questions that are sharp enough and well constrained enough to actually be answered with the right future measurements. Those future measurements will require new missions. The Voyager spacecraft, extraordinary as they are operating on a power budget that continues to shrink. The best current estimates suggest that Voyager 1 may be able to maintain at least minimal science operations until approximately 2025 to 2030, and Voyager 2 perhaps slightly longer or shorter, depending on which instruments are prioritized. After that, the power available from the decaying plutonium generators will fall below the threshold needed to operate any science instruments, and the spacecraft will go silent, still traveling outward into interstellar space, but no longer able to tell us what they are passing through. The loss of the Voyager spacecraft will leave humanity with no in situ measurement capability beyond the termination shock for the first time since 2004, and there is currently no approved mission that will restore that capability within the next several decades. The scientific community has been advocating for a dedicated interstellar probe mission for years. The concept, studied in detail by teams at the Johns Hopkins Applied Physics Laboratory and other institutions, envisions a spacecraft launched on a trajectory optimized for rapid transit to the heliopause and beyond, using a combination of advanced propulsion and a solar gravity assist maneuver to achieve a speed significantly faster than the Voyager spacecraft. The Voyager probes are currently traveling at approximately 35,000 miles per hour relative to the Sun. A purpose-built interstellar probe using a solar gravity assist, where the spacecraft dives close to the Sun and fires its engine at the point of closest approach to gain maximum benefit from the Sun's gravity, could potentially achieve speeds of approximately 100,000 miles per hour or more. At that velocity, the spacecraft could reach the termination shock in roughly 10 years after launch, and the heliopause in roughly 15 to 20 years, compared to the 35 years it took Voyager 1. The scientific payload envisioned for such a mission would be transformative. Unlike the Voyager spacecraft, which were designed primarily for planetary science and whose heliosphere instruments were secondary additions to that primary mission, an interstellar probe would carry a suite specifically designed to answer the questions that the Voyager and Interstellar Boundary Explorer data have raised. Plasma instruments capable of measuring electron and ion distributions with far greater energy and angular resolution than the Voyager plasma science instrument. Magnetometers sensitive enough to resolve the fine structure of the magnetic field at the heliopause transition. Energetic neutral atom images far more sensitive than those on the Interstellar Boundary Explorer, capable of resolving spatial features in the heliosheath at scales that are currently invisible. Dust detectors to characterize the interstellar dust population beyond the heliopause. And ultraviolet spectrographs that could address the New Horizons ultraviolet excess mystery directly by measuring the background at even greater distances from the Sun. The interstellar probe concept received a strong endorsement in the 2024 Heliophysics Decadal Survey. The document, produced every 10 years by the National Academies of Sciences, Engineering, and Medicine, that sets the priority agenda for NASA's heliophysics research program. The survey ranked an interstellar probe as a high-priority large mission for the coming decade. That endorsement does not guarantee funding, and the history of planetary and heliophysics missions is filled with highly ranked concepts that took decades longer than anticipated to reach the launch pad, or never flew at all. But the scientific case has never been stronger, the technological readiness has never been higher, and the urgency created by the impending loss of the Voyager spacecraft has never been more acute. What would an interstellar probe actually find? The honest answer is that we do not fully know, and that not knowing is precisely the point. The history of outer heliosphere exploration has been a history of surprises. The comet-shaped heliosphere was wrong. The smooth, heliopause was wrong. The termination shock as the primary site of anomalous cosmic ray acceleration was wrong. The ribbon was not predicted at all. The elevated plasma temperatures outside the heliopause were not predicted. Every major observational advance in this field has revealed that the actual system is more complex, more structured, and more interesting than the best theoretical predictions. There is no reason to expect that trend to reverse. An interstellar probe traveling through the heliosheath across the heliopause and into the interstellar medium along a carefully chosen trajectory, with modern instruments far more capable than those on Voyager, would almost certainly discover things that are not in any current model. That is not a criticism of the models. It is a statement about the nature of exploration at the frontier of the known. The frontier of the known is a phrase that gets used casually in science communication, but it is worth stopping to consider what it actually means in the context of the heliosphere. The known, in this case, is not simply a geographical boundary, a line in space beyond which our instruments have not yet travelled. It is an epistemological boundary, a limit not just on where we have been, but on what our theoretical frameworks are capable of predicting. When the ribbon appeared in the first interstellar boundary explorer maps, it was not unknown in the sense that nobody had looked in that direction. It was unknown in the deeper sense that the theoretical framework did not contain the concept that could have predicted it. The instruments were looking, and they found something that the theory had no category for. That kind of discovery, the kind that requires not just new data but new concepts, is qualitatively different from the kind that simply fills in a blank on an existing map. Heliosphere science is currently living in the aftermath of several such conceptual discoveries simultaneously. The ribbon requires a new understanding of how the interstellar magnetic field organizes energetic neutral atoms in the region just outside the heliopause. The anomalous cosmic ray acceleration problem requires a new understanding of how particle energization works in turbulent magnetized plasma at the termination shock and throughout the heliosheath. The shape of the heliosphere requires a new understanding of how the interstellar magnetic field pressure, which was underweighted in most early models, shapes the overall structure of the Sun's bubble. And the elevated plasma temperatures outside the heliopause require a new understanding of the energy exchange processes operating at the boundary itself. Each of these problems is being worked on actively by research groups around the world, and progress is being made. But none of them has been fully resolved, and the resolution of each one will likely reveal new questions at a deeper level of the physics. This is the normal condition of science at its frontier. It is not a failure of the field that the models were wrong. It is a success of the observational program that the data was precise enough and comprehensive enough to demonstrate the wrongness clearly. The failure mode in science is not being wrong. The failure mode is being wrong without knowing it, operating on incorrect assumptions without the measurements that would reveal the contradiction. What the Voyager spacecraft, the interstellar boundary explorer, and New Horizons have done collectively and over decades is give heliosphere science the measurements it needed to know specifically how and where the models were wrong. That is an extraordinary gift, and it is one that required patience on a timescale that is difficult to appreciate fully. The Interstellar Boundary Explorer has been collecting data for more than 15 years. The Voyager spacecraft have been operating for nearly 50 years. The scientific returns from these missions have been cumulative and slow building, not dramatic and immediate, and the willingness to invest in that kind of long-term observational program reflects something admirable about the scientific culture that sustains it. There is a dimension of the heliosphere story that goes beyond the purely scientific and touches something more personal, more human in a way that becomes impossible to ignore the longer you spend with this material. The Voyager spacecraft were built by human hands, designed by human minds, launched by human ambition, and are now traveling through interstellar space beyond the sun's domain, in a silence that is almost incomprehensible in its depth. They carry with them the golden records, the gold-plated copper discs, containing sounds and images selected to represent the diversity of life and culture on Earth, included on the spacecraft, on the possibility, however remote, that they might someday be encountered by another intelligence. The golden records were not a scientific instrument. They were a gesture, an acknowledgement that the act of sending something beyond the boundary of our solar system carries a meaning that transcends the measurement of plasma densities and magnetic field orientations. Carl Sagan, who chaired the committee that selected the content for the golden records, described the Voyager mission as a bottle thrown into the cosmic ocean. The metaphor is apt in ways that Sagan may not have fully appreciated when he used it, because the cosmic ocean turns out to be far more structured, far more turbulent, and far more interesting than the term ocean implies. The interstellar medium is not a calm, featureless void. It is a magnetized, partially ionized, turbulent plasma filled with energetic particles, threaded by magnetic fields that connect across light years of space, shaped by the deaths of stars that exploded millions of years ago, and actively interacting with the heliospheres of every star system it surrounds. The bottle Sagan described is traveling through this environment right now, reading it with its aging instruments, sending back data that is still, nearly 50 years after launch, telling us things we did not know. The data stream from the Voyager spacecraft is vanishingly thin by modern standards. Each spacecraft transmits at a rate of roughly 160 bits per second, a data rate so low that a single modern smartphone photograph would take more than 8 hours to transmit at that speed. The signal arrives at Earth with a power of approximately 20 femtowatts, which is 20 times 10 to the power of negative 15 watts, a number so small that it requires the largest steerable radio antennas on Earth, the 70-meter dishes of the Deep Space Network operating at the limits of their sensitivity, to detect it at all. That this signal, carrying irreplaceable scientific data from beyond the edge of the solar system, is successfully received, decoded, and analyzed is a testament to the engineering of both the spacecraft and the ground infrastructure that has been maintained continuously for nearly 5 decades. The Deep Space Network itself is a story that deserves more attention than it typically receives. The network consists of 3 major complexes located approximately 120 degrees of longitude apart around the Earth, in Goldstone, California, near Madrid, Spain, and near Canberra, Australia. This spacing ensures that as the Earth rotates, at least one complex always has a clear line of sight to any spacecraft in the outer solar system. Each complex contains multiple large dish antennas, with the 70-meter dishes being the largest and most sensitive, capable of detecting signals from spacecraft billions of miles away. The network supports not just the Voyager missions, but dozens of active NASA missions simultaneously, allocating antenna time through a scheduling process that balances the competing needs of spacecraft at different distances and in different phases of their missions. For the Voyager spacecraft, Deep Space Network contact is not continuous. The antennas are shared resources, and the Voyager missions receive allocated contact windows that typically last several hours per day per spacecraft. During those windows, data accumulated in the spacecraft's onboard tape recorder is played back and transmitted to Earth, and commands for the upcoming period of operation are uplinked to the spacecraft. Between contact windows, the spacecraft operate autonomously, following programmed sequences that manage their instruments and systems without real-time guidance from the ground. The autonomy of the Voyager spacecraft, their ability to operate reliably for days at a time without human intervention, was an engineering achievement in 1977 that has only grown more impressive with the passage of time and the accumulation of challenges that the aging systems have had to navigate. Consider what the engineering teams at the Jet Propulsion Laboratory have had to do to keep these spacecraft functioning. They have managed the graceful degradation of power-hungry instruments, developing sophisticated load management strategies to keep the most critical systems running as the power budget shrinks. They have diagnosed and repaired software faults on computers running code written in an assembly language that almost nobody in the modern space industry has used in decades, working from documentation that is nearly 50 years old, and from the institutional memory of engineers who have spent their careers with these particular spacecraft. They have managed the thermal environment of the spacecraft as the heaters that keep critical components warm have been progressively shut down to save power, finding creative solutions to keep electronics operating within their temperature limits using the waste heat from other systems. And they have done all of this across communication delays that make real-time problem-solving impossible, requiring every diagnostic and every repair procedure to be planned, simulated, and verified before the commands are sent, because a mistake cannot be corrected in real time. The human story of the Voyager extended mission is therefore not just a backdrop to the scientific discoveries, it is itself a demonstration of something about the nature of long-term commitment in science and engineering, about what institutions can accomplish when they maintain focus and expertise across timescales that exceed individual careers. The scientists analyzing Voyager data today are in many cases not the scientists who designed the instruments or who celebrated the Jupiter and Saturn flyby discoveries in the late 1970s and early 1980s. The knowledge, the expertise, and the commitment have been transmitted across generations of researchers, maintained and built upon, in a chain of scientific inheritance that connects the engineers of the Apollo era to the graduate students publishing heliosphere papers today. There is something deeply human about that transmission, about the way scientific knowledge and the institutions that produce it can persist and evolve across timescales longer than any individual life. And yet, for all the human effort and ingenuity that the Voyager story represents, the universe against which that effort is measured maintains a scale that resists every attempt to make it feel manageable. Voyager 1 is currently the most distant human-made object ever created. It is more than 160 astronomical units from the Sun. It has been traveling for nearly 50 years at speeds that would carry it from New York to Los Angeles in less than 4 seconds. And in the context of the galaxy, it has gone essentially nowhere. The nearest star to our Sun, Proxima Centauri, is approximately 268,000 astronomical units away. At Voyager 1's current speed, it would take approximately 73,000 years to reach it, and Voyager 1 is not even traveling in that direction. The distance Voyager 1 has covered since launch, impressive as it is by any human measure, represents less than 0.1% of the distance to the nearest star. The galaxy is 45,000 light-years from its center to its edge. The observable universe is 46 billion light-years in radius. Against these scales, the achievement of reaching interstellar space, genuine and extraordinary as it is, also carries a humbling reminder of how small the volume of space we have physically touched actually is. This humbling quality is not a reason for despair. It is, if you allow it to be, a reason for a different kind of appreciation, one that takes seriously both the smallness of what we have done and the remarkable improbability that we have done anything at all. The atoms that make up the Voyager spacecraft, the gold in the golden records, the plutonium in the power sources, the aluminum in the antenna dishes, were all forged in stellar interiors or in the explosive deaths of stars billions of years before the solar system existed. Those atoms assembled themselves over 4.5 billion years of geological and biological evolution into living creatures capable of curiosity. Those creatures developed language, mathematics, physics, and engineering. And then, in a cosmically instantaneous moment, they built two machines and threw them beyond the boundary of their star's domain, attached to one of them a record of their music and their laughter and the sound of wind and surf, and sent it into the dark. That this happened at all, that the universe produced within itself something capable of studying itself, is the deepest mystery in all of this. Deeper than the ribbon, deeper than the shape of the heliosphere, deeper than the anomalous cosmic rays or the elevated plasma temperatures or the unexplained ultraviolet background. What NASA has found beyond the edge of our solar system is not a simple answer to a simple question. It is a set of discoveries that have made the question more complex, more layered, and more interesting than it was before the measurements were made. The heliosphere is not the neat, comet-shaped bubble the models predicted. It is a dynamic, asymmetric, magnetically complex structure whose shape reflects the ongoing negotiation between the Sun's outward pressure and the interstellar magnetic field's organizing influence. The heliopause is not a clean, passive boundary. It is a site of active energy exchange, particle acceleration, and magnetic complexity, where two fundamentally different plasma regimes meet and interact in ways that our theoretical frameworks are still learning to describe. The interstellar medium just beyond the heliopause is not the quiet, featureless void that early models assumed. It is a structured, magnetically organized environment that bears the marks of the heliosphere's influence extending outward, and whose own properties, temperature, density, and magnetic field orientation differ from the model predictions in ways that are still being understood. The ribbon remains one of the most striking symbols of how much we have yet to learn. It arcs across the energetic neutral atom sky, bright and structured and geometrically precise, a feature so visually dramatic that it would seem almost designed to draw attention to itself, and yet its detailed formation mechanism remains under active debate more than 15 years after its discovery. It is telling us something specific and important about the relationship between the heliosphere and the local interstellar magnetic field, something that is written clearly enough in the data to be undeniable, but not yet clearly enough in the theory to be fully explained. The ribbon is a question mark drawn across the sky in particles, and answering it fully will require the kind of new measurements that only a future interstellar probe mission can provide. The anomalous cosmic ray puzzle, the elevated temperatures, the magnetic field behavior at the heliopause, the non-comet shape, the ultraviolet excess, the turbulent heliosheath, the asymmetric breathing of the boundary with the solar cycle, these are not a list of failures. They are a map of the territory that remains to be understood, a detailed inventory of the specific ways in which our models of the heliosphere's outer boundary fall short of capturing the actual physics. Science rarely provides a more valuable product than a precise inventory of its own incompleteness, because that inventory is the agenda for the next generation of research. Every anomaly on that list is a door, and behind each door is a piece of physics that, once understood, will change not just our picture of the heliosphere, but potentially our understanding of how stellar systems in general interact with their galactic environments. Our Sun is not unique in having a heliosphere. Every star that produces a stellar wind produces a similar bubble, an astrosphere, within which the star's physical presence extends against the surrounding interstellar medium. There are hundreds of billions of stars in our galaxy, and each one with a significant stellar wind has its own version of the heliosphere, its own termination shock, its own equivalent of the heliopause, its own interaction region with the surrounding interstellar gas and magnetic field. The physics we are learning about our own heliosphere is therefore not just local knowledge. It is the physics of stellar astrospheres in general, applicable in principle to every star system in the galaxy, including the star systems that may harbour planets and the planets that may harbour life, and the life that may one day look up at the night sky and wonder where its own solar system ends and the galaxy begins. There is something quietly extraordinary about that chain of implication. The measurements that Voyager 1 is making today in the interstellar medium, more than 160 astronomical units from the Sun, in a region so remote that its radio signal takes 22 hours to reach Earth, are measurements that bear on the question of how stellar systems are coupled to their galactic environments across the entire galaxy. The plasma density Voyager 1 is sampling, the magnetic field direction it is measuring, the energetic particle distributions it is characterizing. These are samples of the interstellar medium that surrounds not just our solar system, but the stellar neighborhood that contains hundreds of other star systems within a few dozen light years of the Sun. Understanding the physics of this environment, how it shapes and is shaped by the heliospheres of the stars embedded within it, is understanding something about the galactic context of all those other stellar systems simultaneously. We are, in a sense that is both literal and profound, measuring the ocean our solar system swims in. And what we are finding is that the ocean has currents and structure and a magnetic skeleton that organizes it across vast distances, and that our solar system's presence within it leaves a wake, a disturbance, a signature that extends outward from the heliopause into the surrounding interstellar medium in ways we are only beginning to map. The heliosphere is not a sealed container, isolated from its environment. It is a permeable, dynamic interface, breathing with the solar cycle, shaped by the interstellar magnetic field, exchanging energy and particles with the surrounding medium, and leaving its mark on the interstellar environment, even as that environment leaves its mark on the heliosphere. What comes next in this story depends on decisions that have not yet been made, funding that has not yet been allocated, and missions that have not yet been built. The scientific community has made the case clearly and repeatedly for a dedicated interstellar probe. The data from the Voyager spacecraft and the Interstellar Boundary Explorer has made the scientific need undeniable. The technology to build a faster, better instrumented mission exists or is within reach. What remains is the institutional will to commit to a program whose full scientific return will arrive decades in the future. whose principal investigators have not yet been selected, and whose discoveries cannot be predicted in advance precisely because they will come from a region of space and a physical regime that our current understanding does not fully describe. That is always the character of genuine exploration. The destination is known only approximately. The journey takes longer than any individual career. And the discoveries, when they come, are never quite what was expected. And yet the silence that surrounds the Voyager spacecraft is not an absence. It is a presence, a physical environment of extraordinary complexity that the spacecraft are sampling one measurement at a time, building a portrait of the interstellar medium that will serve as the baseline against which all future observations of this region will be compared. The silence is full of magnetic fields threading through the plasma at orientations that tell us about the history of the local bubble, about the supernova explosions that carved this cavity in the interstellar medium millions of years ago, about the way the energy released by those dying stars was distributed through the surrounding gas and organized into the large-scale magnetic structure that we are now, for the first time, sampling directly. Every magnetic field measurement Voyager 1 makes is a data point in a map of the local galactic environment that no telescope, however powerful, could produce remotely. You cannot image a magnetic field from a distance, you have to be there. Being there in the context of interstellar space is a phrase that carries an almost unbearable weight. When you sit with it long enough, Voyager 1 is there. It is physically present in the interstellar medium, moving through it, displacing it, measuring it from the inside. There is no other human artifact anywhere near it. The nearest human-made object to Voyager 1 is Voyager 2, travelling in a completely different direction at a similar distance, equally alone, equally silent except for that faint 20 femtowatt whisper aimed back at the sun. Between the two Voyager spacecraft and every other object humanity has ever built lies an unimaginable volume of interstellar space, completely untouched by human presence, threaded by magnetic fields and populated by energetic particles and drifting neutral atoms and the occasional dust grain moving at interstellar velocities. It is the universe as it has been for billions of years before life existed to observe it, and two human machines are passing through it right now, reading it, measuring it, reporting back. The reporting back will not last indefinitely. The plutonium in Voyager 1's generators was refined and shaped into its current form by human hands at a facility in Idaho in the early 1970s. Since the moment it was sealed into the generator housing and bolted to the spacecraft, not a single human hand has touched it. It has been decaying continuously for nearly 50 years, releasing heat that has been converted into electricity that has powered the instruments that have returned data from Jupiter, from Saturn, from the termination shock, from the heliopause, and from the interstellar medium beyond. That decay will continue inexorably and without any possibility of intervention until the heat output drops below the threshold needed to keep the spacecraft systems warm and functional. When that happens, components will begin to fail as temperatures drop below their operating limits, and the spacecraft will go quiet. Not dramatically, not with any announcement. It will simply stop transmitting, and the silence that follows will be permanent. What happens to Voyager 1 after it goes silent is a question that has a precise physical answer and a less precise, but more affecting philosophical one. The physical answer is that the spacecraft will continue traveling outward through interstellar space at roughly 38,000 miles per hour, decelerating extremely slowly under the gravitational influence of the Milky Way's mass distribution, for an effectively unlimited period of time. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 946, a dim red dwarf in the constellation Camelopardalis. It will not enter that star's solar system. It will pass through its outer gravitational neighborhood and continue outward. In approximately 300,000 years, it will pass within about 8 light-years of the star Sirius, the brightest star in our night sky. It will never stop. There is nothing in its path capable of stopping it. The golden record it carries will outlast the sun, outlast the solar system, outlast, possibly, the galaxy itself. Travelling through a universe that will be unrecognizably different from the one in which it was made, carrying the sounds of Earth into a future so distant that the word future loses its meaning. The philosophical answer to what happens after Voyager goes silent is harder to articulate, but impossible to ignore. There is a version of this story in which the loss of the Voyager signal is simply an engineering event, a power budget calculation reaching its inevitable conclusion, an old spacecraft finally succumbing to the entropy that has been accumulating in its systems for half a century. And that version is true, as far as it goes. But there is another version in which the loss of the Voyager signal represents something more than an engineering event, in which it marks the end of a specific chapter in the human relationship with the cosmos, a chapter that began in 1977 when 2 machines left the surface of a small rocky planet orbiting an unremarkable star and began the first physical journey beyond the boundary of that star's domain. That chapter will not end when Voyager goes silent, not really, because the data it has returned, the discoveries it has enabled, the questions it has sharpened into precision will continue to shape the science and the imagination of the civilization that built it for as long as that civilization persists. The spacecraft will go silent, but the knowledge it carried back will not. This is, in the end, what exploration means at the deepest level. Not the physical act of travelling to a place, though that act has its own irreducible value and its own irreplaceable data returns, but the transmission, the insistence on sending back what was found, on making the knowledge available to the civilization that made the journey possible, on turning the private experience of a machine passing through the interstellar medium into a public inheritance that belongs to everyone who has ever looked up at the night sky and wondered what lies beyond the last planet. The Voyager spacecraft were built with public resources, launched with public support, and maintained for nearly 50 years with public funding. The data they return belongs, in the most meaningful sense, to the public that made them possible. And what that data says, what it has been saying with increasing clarity and increasing complexity for nearly 5 decades, is that the universe beyond our solar system is real and present and measurable and stranger than we thought and worth understanding. The interstellar medium that Voyager 1 is currently passing through was here long before the sun ignited, long before the Earth formed, long before the first living cell divided in some warm, ancient sea. It will be here long after the sun has exhausted its hydrogen fuel and expanded into a red giant that swallows the inner planets. The magnetic fields threading through it were laid down by processes that began billions of years before the solar system existed. The energetic particles streaming through it were accelerated by supernovae whose light reached Earth thousands of years ago and has long since faded. We are, in sampling this environment for the first time, reaching back through time as well as outward through space, touching a medium that has been present and essentially unchanged on the scale of a human lifetime since before there were humans to measure it. And now, at last, we are measuring it. Two machines, built from the knowledge of generations, powered by the decay of atoms forged in a dying star, guided by mathematics developed over centuries of human thought, are passing through it right now. Their instruments are aging, their power is fading, their memory chips are failing one by one, and they are still transmitting, still measuring, still sending back data across 22 hours of empty space, data that arrives at the 70-meter dishes of the deep space network as a whisper 20 times quieter than the faintest signal a modern phone can detect. And that whisper contains the actual measurements of the interstellar medium, the actual magnetic field strength, the actual plasma density of a place no human will ever visit, and that only one human-made object has ever touched. That is what NASA has found beyond the edge of our solar system. Not a final answer, but a deeper question. Not a boundary that ends the story, but a threshold that opens it. The heliopause is not a wall, it is a beginning. The first page of a chapter in the story of our solar system's place in the galaxy that we are only now, with instruments built from silicon and aluminum and the accumulated knowledge of generations beginning to read. We do not yet know what the chapter says, but we are listening across distances that humble every human ambition to the faintest possible signal from the most distant place we have ever reached, and it is telling us with the patient, precise language of physics that the universe beyond our solar system is stranger, richer, and more magnificent than we knew.